Alright, this is converting polar to rectangular, rectangular to polar. These are all the formulas and a picture associated with rectangular relationships to polar coordinate relationships. So this coordinate here is represented by xy, but it's also represented by the radius of this triangle and this angle near the origin. So here I want to convert this rectangular form equation into polar form. So in other words, I want to get rid of x's and y's and replace them with r's and thetas. So these formulas are the only things you can work with. So we can do a direct substitution. Y is equal to r sine of theta. So I can substitute that in here. Times 2, or I'm sorry, equal to 2 times x. Well, x is equal to r cosine theta. And then that minus 3 kind of just hangs out. All right, your goal here is to get the r's by themselves so you can have an equation written in r in terms of theta. So I could do two things. I can move him over to the other side, but then that leaves a negative 3. So I'm going to play one of my switch tricks, and I'm going to take this 3 and this r sine of theta and just switch their positions. So this becomes 3 is equal to 2r cosine theta minus r sine of theta. And again, my goal is to solve for this r. So the next step would be to factor it out. So if I kick out r, left behind is 2 cosine theta minus sine of theta. And then solving for r, I just need to divide that across. So I get 3 over 2 cosine theta minus sine of theta. And there's the polar form of the equation of a line. Now out of the two, which one is much more easy to work with? Well, of course, y equals mx plus b is much nicer to look at. We know what the slope is, we know where the intercept is, and all things are good. In this form, things are a little bit harder to work with, but in upper level maths, sometimes converting into polar is very useful. All right, let's try another example. This one's a little more complex, but it gives us some more tricks to play with. Again, these are the only formulas you can work with. You could directly substitute in r cosine theta and r sine theta like last time, but you'll recognize that these things have squares, and eventually you're going to have an x squared and a y squared, so I'm leaning towards possibly using this formula. So before I start doing these substitutions, I'm going to expand this out. So this becomes x squared plus y squared minus 4y plus 4 is equal to 4. Now the 4's are going to cancel, which is nice. This x squared y squared in the front, I can substitute x squared y squared directly into r squared. But once I do that step of moving into polar, I want to make sure I get rid of all the x's and y's. So this first part just becomes r squared minus 4 times, and I'm going to substitute away the y using r sine theta, and the 4's disappeared. And you get that. All right, next step would be I really want to solve for r. So again, I'm going to factor it out. So I get r times the quantity r minus 4 sine of theta, and is equal to 0. And I'm going to, set each factor equal to 0. Now, r is equal to 0 is the origin, and it's not really the equation I'm looking for here. This thing up here is a circle that's centered at 0, 2. So if you want a little picture of it, 0, 2 is here. And you're going to have a circle of radius 2 around it. So we're looking for the top half, what I call a top circle. So r equals 0 is definitely not that. R equals 0 would be radius 0, which means it doesn't even exist. All right, so r minus 4 sine theta is equal to 0. We would get r equals 4 sine of theta. So this equation is the circle that is centered at the coordinate 2, 0, 0, 2, 0, 2, and has a radius of 2. Kind of neat that it became a nice simple equation. All right, let's go the other direction. Same idea. All we have are these formulas to work with and possibly this picture. Haven't we really used the picture yet? So to convert r, there is no direct relationship between r and anything, but there is a direct relationship between r squared and x's and y's. So the trick we're going to use here is we're going to multiply both sides by r, which is totally legal as long as r is not equal to 0. Well, even if it's equal to 0, but it's kind of pointless if it is. So this side becomes r squared is equal to r cosine of theta. And r squared, if we go into rectangular coordinates, is x squared plus y squared. And r cosine of theta is x. So we get this equation, which is also a circle. We can kind of manipulate it to see what kind of circle it is. This is x squared minus x, leave a space, plus y squared is equal to 0. If we complete the square, this becomes half of that -1, negative a half. We'll add on the square of that, which is a quarter to both sides. And this becomes x minus a half, all squared, plus y squared is equal to a quarter. So this is a circle whose center is at a half comma 0, and whose radius is a half. So it's just a little baby circle. Okay, one more. This one's kind of weird looking, and if you start attacking it wrong, it becomes really messy. So again, we're going to use that trick of looking for an r squared. So I'm going to multiply everybody by r, and it works out rather well. So we have here r squared is equal to 5 r cosine of theta minus 2r sine of theta. And again, r squared is going to become x squared plus y squared. And this will become 5, and r cosine of theta is x. And r sine of theta over here is the same thing as y. So we're going to get 2y. And again, this is a circle. It's a lot messier, and I'm not going to go through all the work involved to find the center and radius, but you can move the 5x and the 2y across, complete the square on both of them, gives you lots of fractions. But this is a nice rectangular form of the original equation up here.